Okay, so today we have to study retarders. So आज क्लास ना थोड़ा छोटा ही होगा, 1 hour का ही होगा, तो जल्दी जल्दी पढ़ते थोड़ा सा. Okay, so what are retarders? So retarders are a class of optical elements that change the polarization of an incident wave. Okay, so example would be that I can have a quarter wave plate, or I can have a half wave plate, or I can have a Fresnel ROM, but this we don't have to study, but it's also one kind of a retarder. Okay, so for us, most important elements are quarter wave plate and half wave plate. So we already know that a quarter wave plate and a half wave plate will be made up of some kind of a birefringent material, so that when any incident light is incident on this quarter wave plate and half wave plate, so one part of the, basically what we'll do is we'll take a birefringent crystal and we will polish and cut the crystal in such a manner so that the optic axis of that crystal is going to be parallel to the plane of incidence. So if this is my crystal, so I will make sure that optic axis is either like this or like this. I'll cut and shape the naturally occurring crystal in this manner so that I can make a quarter wave plate and a half wave plate. So I will change the thickness of this crystal, or I will change the crystal itself so that the phase or the retardation that I can produce between the ordinary wave and the extraordinary wave is equal to, either 90 degrees or 180 degrees, and that will correspond to a quarter wave plate, half wave plate. So this working principle we already discussed in the last class. So I will just write down a couple of formulas that we should remember. So one thing I told in the last class was the optical path difference. Okay, so I wrote capital lambda is equal to, I think Z I wrote, which was the distance or the sort of the thickness of the plate or the crystal that we are using. And this was multiplied with the birefringence. Okay, so this is the magnitude only I'm taking. So N naught can be greater than NE, or NE can be greater than N naught, depending on the type of birefringent material I'm dealing with. So I've taken mod. So I'm only taking the magnitude and not the sign, and I'm finding out what is the optical path difference. So corresponding to this optical path difference, I can have a phase difference. So this is the phase difference which is introduced between the ordinary and the extraordinary ray. So whatever my incident beam has fallen onto this crystal. So this was my, let me stop saying crystal and let me start saying plate. Okay, so I have some retarder, I have some kind of a half wave plate or quarter wave plate, and I'm assuming that this is my optic axis. Okay, so the incident beam is, falling like this, making some angle theta with respect to the optic axis. Then I said that I will take one component which is parallel, oriented in the direction of the optic axis, and I will take one component which is oriented perpendicular to the optic axis. So the E ray was the one which is parallel. So E ray was parallel to the optic axis, and the O ray was perpendicular to the optic axis. So as this beam was going through the length of the crystal, these two rays, because they are traveling with different velocities, will gain a different amount of phase difference. And so this phase difference is between the O ray and E ray. So I can call it delta phi. Okay, so delta phi is equal to 2 pi by lambda naught and this capital lambda. So this capital lambda is the optical path difference. So now there is one thing that should be immediately clear to me, that depending one half wave plate or 1/4 wave plate will not work for all wavelengths, because the phase difference is here dependent on the lambda. Okay, so if I want to, it's dependent on the wavelength. So if I want to work with, let us say, red light or red laser, so I will have to use the half wave plate and the quarter wave plate for that red wavelength. For lambda is equal to 633 ke liye, I'll have to find out what is the birefringence I want, or what is the thickness I want, or what is the optical path difference I want, so that my delta phi comes out to be either 90 or comes out to be 180, depending on what type of retarder I want to make. Okay, so this is one thing that we should remember, that this phase difference is not same. It has a dependence on wavelength. So one quarter wave plate or half wave plate is not going to work for all the wavelengths. Okay, so if red ke liye, if I'm getting 90 degrees delta phi, maybe if I will use another green light, maybe I'll get something greater or larger than delta phi. वो calculate करना पड़ेगा. So मतलब it will not give me the complete effect of a quarter wave plate in that sense. So this is one thing. And the second thing is, till now we have only considered the input light to be a P state, to be a plane polarized light. Okay, so in this diagram, when I'm considering this incident field, so this is a P state that I'm considering, but there can be other types of incident light also, that I can have circularly polarized light, which is incident on a retarder, or I could have an elliptically polarized light, which is incident on a retarder. So depending on what is the polarization state of the input light and what is the wavelength, you would get different type of polarization states on the other end of the retarder. So after passing through the retarder, depending on all these things, you will produce different types of polarization states on the other end. Okay, and another thing that we should just make a note of, that passing through a quarter wave plate or a half wave plate. So one thing is that so first thing that we have to remember in mind is that this is, the retarders are chromatic. Okay, so chromatic means that they are dependent on lambda. Okay, the second thing, so you understand what I mean by dependent on lambda. So each, depending on different lambda, I should use different half wave plates or quarter wave plates. The second thing is that the output polarization state depends on the incident beam also. So I always have to, I cannot think that every time if I'm using a quarter wave plate, I'll get circularly polarized light. That is only true when I have a P state, and that too when the theta is 45 degrees. So I'll write down all these cases for you in a moment. But I just want to make a note here so that you remember that, okay? And the third thing is that there is no loss of intensity. On passing through an ideal retarder. So there is no ideal retarder in real life, but the principle of a retarder says that only this delta phi phase difference is introduced. There is no change in the intensity in any way. Like a polarizer reduces in intensity of a unpolarized beam, and of a polarized beam, we have to apply Malus law, right? When we use a polarizer. So polarizer also changes the polarization, but it also reduces the intensity by according to the Malus law. But here the polarization state is changed, but we do not have any loss of intensity. So that is one thing we should remember. Okay, so after that, what we have to do is we have to look into these retarders one by one. So first is a full wave plate, which is not used anywhere. So full wave plate means that this del phi is equal to 2 pi. So basically my E ray and O ray are back into phase after they have crossed the retarder. On the other end of the retarder, on the output end of the retarder, I get back the same polarization. So here O and E ray are back in phase at output. Okay. So there is no change in the polarization state, and therefore this kind of a wave plate is not useful to us at all. Okay, so this is just a concept. We don't really make these full wave plates because they really are not doing anything. They are not reducing the intensity. They are not changing the polarization. So basically we have the same wave in a way. Okay, so okay, so one more thing I want to say. Let me write it here. So the second case is that we consider a half wave plate. So this is written as HWP in short form. Okay, so one small thing which I want to write is the optic axis jo hota hai, see, this optic axis is OA. Okay, so OA here represents the optic axis. Okay, so in most of the cases, we are discussing a calcite crystal, which is a negative uniaxial crystal. So negative uniaxial crystal ka matlab hai, let me write it here. So my optic axis is also called fast axis. Okay, but optic axis ke parallel kaun sa ray ja raha hai? Extraordinary ray ja raha hai, right? So E ray is parallel to my optic axis to OA. Okay, this is what I've said. But optic axis is also called fast axis in certain cases. So what does that mean? So this comes from this fact that if I take a calcite crystal, so calcite crystal is a negative uniaxial crystal. So what that means is that the velocity for the extraordinary ray is greater than the velocity of the ordinary ray. Okay. And because the E ray is traveling parallel to the optic axis, therefore the optic axis is sometimes also called fast axis. And the O ray is perpendicular to the optic axis. So therefore, if this is my optic axis, I will say that this is my fast axis. And any direction which is perpendicular to this. So the direction which is perpendicular to this, I will say that this is the slow axis. But what does this mean? This means this, that in a negative uniaxial crystal, and mostly we are talking about calcite when we are talking about retarders, my VE, the direction in which the E ray is moving, coincides with the optic axis, and therefore we say the optic axis to be the fast axis, and the direction perpendicular to it is the slow axis. So if in a question, rather than talking in terms of optic axis, the question says the slow axis of the crystal or the fast axis of the crystal. So this should be sort of clear to us that, they mean the same thing. At least this much should be clear to us. And any direction which is perpendicular to the optic axis would correspond to this slow axis. So if the orientation of optic axis is given or the orientation of slow axis is given, we can find out the orientation of optic axis, because everything in retarders happens with respect to the optic axis. तो वो हमें निकालना बहुत जरूरी है in a question कि which is the optic axis. अगर fast axis बताया क्या है तो वही optic axis है. If slow axis is being told, so then the optic axis is the direction which is at crossed angle, or which is making a 90-degree angle with respect to the slow axis position. Okay, so this is one thing we should know. So for a half wave plate, the formula for del phi. So what is del phi? So del phi for a half wave plate should be equal to pi or multiples of pi. So it should be either pi or 3 pi or 5 pi, like that. So it should be like half a circle, half a rotation. So it can be one full rotation plus half a rotation, two full rotations plus half a rotation, like that. Okay. So the formula for the optical path difference, this one, okay, जो capital lambda है, उसका formula हो जाएगा इसके लिए, that Z NE minus N naught. Okay, so here, see, यहाँ पे do not get confused that I am writing NE कभी पहले और N naught कभी पहले. It doesn't matter. You only have to take the difference between the two. Here I have written it like this because maybe that, no, I've written it wrong. It should be N naught minus NE. वही मैं अभी सोच रही थी, because we are dealing with a uniaxial crystal. And जैसे मैंने बोला that VE is greater than V naught. That means that NE here is actually less than N naught, right? So therefore, यहाँ पे ऐसे लिखा है, but you don't have to remember this per se. We always have to take the mod of the difference. So anyway, it will work out fine. So this should be equal to 2m plus 1 lambda naught by 2, where m can be 0, 1, 2, and so on. Okay, so this is basically telling you the path difference. So this formula is for the optical path difference. And if I will multiply the optical path difference with k is 2 pi by lambda, that will give me del phi. So what is del phi? So this is capital lambda. So del phi is 2 pi by lambda naught multiplied by this. Okay. So if the question asks you either of these two things, that find out the optical path difference required to make this kind of a plate or something like that for this particular lambda, you can use the above formula. And if they ask you, if they tell you that this is the del phi we want, so this is the value of the phase difference that we want, then find out that what should be the optical path difference, or what should be the birefringence, or what should be the thickness of the crystal. So what is Z here? Z is the thickness of the retarder, या फिर the distance traveled. Okay, so if we want to see something, if we want to see even inside the crystal, maybe पूरा length हमने travel ही नहीं किया, we are still inside the retarder. So if some distance is given, then I will just plug in that value of distance, that what is the length that the beam has traveled in the retarder. Okay, so we might also inspect the polarization inside, or we might also inspect it outside if the question gives you like that. But mostly they will always ask you on the output end. So you have to just take Z to be the thickness of the retarder in that case. Okay. So now we have to understand that what would a half wave plate do. Okay. So let us consider that. So now what I'm considering is that if this is my retarder, so I'm saying that this is my optic axis. Okay, so parallel to the plane of the plane of incidence on this retarder, and then I'm saying that my beam is sort of falling something like this. And this is some angle theta it is making with respect to the optic axis. Okay, so now I want to inspect this kind of a case, but I might also want to inspect that what happens if the input light is changed. So currently, this is what you should imagine when I'm talking about a P state. And when I'm talking about a circularly polarized or other kind of beam, so we'll discuss that in a moment. But always I'm considering that the optic axis is parallel to my x-axis. Okay. So now what I have is, let us do is my case number 1. So case number 1 is that my incident light is actually some P state. So ये हमने last class में भी discuss किया था, but अभी थोड़ा अच्छे से कर लेते हैं. So I have a half wave plate. Okay, so right now what I have shown is that this is my half wave plate. So it has a certain thickness associated with it. So this thickness is actually this thickness. Okay, so I'm just looking at it. It's placed like this. So I'm looking at the side of it so that I see the thickness. This is not the front of the wave plate. Okay, so the beam is incident like this on the wave plate, and this is the side portion is what I'm looking at right now. Okay, so then let us make some input beam. Okay, so this is my या ऐसे समझ आएगा, एक सेकेंड. ठीक है, आ जाएगा. तो अब क्या है, this is my x direction. So this is my x, this is my y. Okay, so this is also, I'm not looking at it straight, but this is also slightly rotated. Okay, can you understand? I'm not looking at like this, but like this. So z is going like this inside the paper, and y is like this. So now my beam is incident like this, so that it is making some angle theta with respect to the x-axis, but optic axis is also parallel to the x-axis. So in a way, this is coming, this is my wave plate, the beam is coming like this, and the beam is making an angle theta with respect to the x. Okay, you can visualize it. So now this is my half wave plate. So now half wave plate क्या करती है? हाफ वेव प्लेट में जो एक कंपोनेंट होगा बीम का, which is along the x-axis, which is parallel to the optic axis, is going to move faster compared to the other component. ठीक है, so I will introduce a phase difference of कितना इसमें pi, right? It's a half wave plate, so 2 pi का half करना है. So I will introduce a phase difference of pi between these two components. So इसका एक component x के along है, which will propagate inside the half wave plate like a E wave. So it will move faster, and the other component is now oriented along the y direction, which is perpendicular to the optic axis. So it will behave like an ordinary ray, and it will move slightly slower because it's a uniaxial, negative uniaxial crystal right now. Okay, in a positive, reverse would happen, that the O ray would move faster and the E ray would move slower in that case. Okay, so so then in that case, the concept of fast axis and slow axis would be slightly different. So unless and until it is not specified to you that it's a negative or a positive crystal, then always the fast axis means the optic axis. For your exam, the fast axis would always be the optic axis. बहुत ज़्यादा उसमें सोचना नहीं है, ठीक है? इतना confuse मत होना. So now what will happen is, if I sort of write that what is this state? So I can write that my input beam, my E field, is something like EOX I cap plus EOY J cap and cos kz minus omega t. So it's moving in the Z direction. And EOX क्या होगा फिर if I'm taking these components? So this distance is EOX then, and this distance is EOY, right? So now what is going to happen is that one beam is going to travel faster, and I'll end up introducing a pi ka phase between the two components. So what will happen is on passing this side, so I'm saying delta is equal to pi. Why am I saying delta is equal to pi? Delta means the phase difference between the two components after they have passed. Okay, I'm writing it not equal to del phi because in other cases you will see that delta is not necessarily equal to del phi. डेल्टा का मतलब होगा कि what is the final phase difference in the output plane. ठीक है, it is not the phase difference produced by the half wave plate. हाफ वेव प्लेट हमेशा पाई का ही डेल्टा मतलब पाई का ही फेज डिफरेंस प्रोड्यूस करेगी, but depending on the input state, this delta may be equal to that or may be slightly different than that. Okay, so this delta here means that the output plane में the phase difference between the two components. So now what will actually happen is that my electric field will actually get rotated by an amount of theta, 2 theta, and I will get something, it will get rotated about the optic axis. So what will happen is that if this is my system, so initially my field was something like this, making theta, and this was my optic axis, this was my X. So now I will get something like this, so that it's rotated like this. Okay, so अब क्या हो गया है, मैंने total rotation कितना किया, यहाँ से I rotated it till here. So I did a rotation of 2 theta. 2 theta से मैंने उसका orientation change किया. But if I look at the components, so what have I done? If I look at the components, so if I look at this and if I look at this, so अब क्या है, ये EOX और EOY का वैल्यू तो मैग्नीट्यूड तो चेंज नहीं होगा बिकॉज आई जस्ट डिस्कस्ड इंटेंसिटी में कोई फर्क नहीं आता बिकॉज of a retarder. But what I have now changed is that the EOX is still the same. So यहाँ पर my electric field which is coming out, so EOX is still this, but EOY has actually become this, right? Because now EOY ये है, this one, so which is negative, in the negative direction. So in a way, what I have done is I have ये जो pi का phase difference है, that can come in either of the two components depending on how the optic axis is oriented. If optic axis was parallel to the y-axis, then I would have introduced a negative component in the ith, एक negative sign में ith component में add कर देती. But otherwise, you know, मतलब you just have to think that an extra cos of pi is getting multiplied with this. So an extra phase is getting multiplied with this. Or you can add an extra, ये जो cos kz minus omega t है ना, इसके साथ एक extra pi का phase add कर सकते हैं. And then we'll see that only in one component we will have this phase. एक के लिए तो cos of kz minus omega t हो जाएगा, दूसरे के लिए cos of kz minus omega t plus pi हो जाएगा. So that plus pi का एक minus sign बाहर आ जाएगा. And depending on how my optic axis is oriented, I will sort of flip the polarization. Flip in the sense I will rotate it. So agar pehle my beam was sort of oriented in the first and the third quadrant, and if the optic axis is parallel to the x, so I will flip it like this, so that now it will be oriented in the fourth and the second quadrant. Now the value of how you are flipping it matters, because question में क्या दिया है, let us say कुछ input electric field दिया है जो मैंने यहाँ पे लिखा है on the left hand side, ठीक है, and they tell you that some half wave plate is inserted. So on the output what would you get? अब ये जो थीटा है ये 30 डिग्रीज भी हो सकता है, 60 भी हो सकता है, कुछ भी हो सकता है. So if it is 30, so we only have to rotate it by 60 degree, and then we have to use that 60 degree in other calculations. ऐसा होता है that you have to use this, how much rotation or what should be the placement. So this is how you have to use. If you will flip it the other way, so then you will flip it by 120 degrees, and then you will use 120 in your calculations. मतलब 2 theta is equal to 120 लिख दोगे, and then from there you will try to find out something, and then you will make a mistake. So always remember that this flipping has to be done, with respect to the optic axis. It is flipped about the optic axis, not about the other axis, or the slow axis के about नहीं, fast axis के about it is flipped. ठीक है, so just make a note of that कि यहाँ पर जो half wave plate होगा rotates the input P state by 2 theta about the optic axis, where theta is the angle, the incident beam makes with the optic axis. Okay, so अब ये तो easy case था, हमने कल भी पढ़ा था. Second case हो सकता है that my incident light is not a P state, but it is a circularly polarized light. So incident light जो है half wave plate के ऊपर is now in RCP or an LCP. So it's either a R state or a L state or a circularly polarized light with right-handed or left-handedness. Okay, so what will happen is, if I will, let us see what will happen. So if I have a half wave plate again, okay, so input में मेरे पास let us say LCP light incident है, ठीक है, I have a, या RCP लिख देते हैं because मैंने RCP का expression लिखा हुआ है. So let us say RCP है यहाँ पे. So RCP हमने कैसे लिखा था? We wrote the electric field like this. Okay, so this is the incident electric field, which is a beam which is right circularly polarized. So now this is incident on my half wave plate. So what will I get on the output? So half wave plate क्या करेगी फिर से? One of the components, either one of the components is going to, depending on how my optic axis is oriented, depending on that, I will I'll introduce a phase of pi in one of these components. So what will happen is I will flip the handedness. So if RCP is incident, I will get LCP here. And if the LCP is incident, on a half wave plate, it will give me RCP. Okay, so let us see कैसे. So if I consider LCP में क्या होता है, यहाँ पर माइनस साइन हो जाता है. It becomes I cos kz minus omega t minus j sin kz minus omega t, है ना. So if let us say कि my my optic axis is oriented in such a way that जो मेरा ये yth component है, it gains a phase of pi. So if this gains a phase of pi, so what I'm saying is that this gains a phase of pi, because I can add pi to दोनों में से किसी में भी add कर सकती हूँ, right? So I'm choosing this, and what this becomes is it becomes sine kz minus omega t plus pi. It becomes this. So which is nothing but minus sine kz minus omega t. Okay, so basically I have introduced a minus sign, therefore this will give rise to an output field. So यहाँ पर output में क्या मिल जाएगा? I'll get E naught I cos kz minus omega t minus j sine kz minus omega t. And what is this? This is nothing but the expression for a left circularly polarized light. Similarly, I can check for input when input is LCP and output will come out to be a RCP light. Okay, so this is one thing that we should remember, that if I want to change the handedness of a light, of a circularly polarized light, then which component do I need to use? I need to use a half wave plate. Okay, so एक second. And this will also be true for a elliptically polarized light. So case 3 हो सकता है that incident light, यहाँ पे ना बड़ा बड़ा लिख लेते हैं, that RCP या LCP दोनों के दोनों हाफ वेव प्लेट के थ्रू जाएंगे. So they will be LCP and RCP में they will be changed. So half wave plate changes the handedness of circularly polarized light. CPL means circularly polarized light. So this is something which is important. So we should remember this. Okay. So the same is true for an incident light, which is elliptically polarized. So elliptically polarized light, elliptical light. So this can also be either right or left-handed. ठीक है, so इसमें भी क्या होगा? See, हाफ वेव प्लेट ने क्या किया? सिर्फ हैंडेडनेस चेंज किया, बट पोलराइजेशन चेंज नहीं किया. पोलराइजेशन अभी भी सर्कुलरली पोलराइज्ड ही है, बट ओनली द राइट हैंडेड और द लेफ्ट हैंडेड वो एक मतलब that got reversed. Right became left, left became right. But the actual nature of the beam, half wave plate is not changing the polarization of the beam in that way. जैसे हमने ऊपर देखा कि जब इंसिडेंट लाइट P स्टेट था तो वो P स्टेट में ही बाहर आएगा, बस वो रोटेट हो जाएगा by some angle. ठीक है, but it will always give you output in the same state of polarization, only it will rotate. यहाँ पे क्या हुआ? P state को उसने rotate कर दिया. So if the question says that we want to rotate by some amount, so it should be clear that we do not want to change the polarization state. We just want to rotate the electric field by some amount. So we'll have to use a half wave plate, right? Similarly, अगर मैं इंसिडेंट लाइट देखूं जब सर्कुलरली पोलराइज्ड है तो क्या हुआ? आई एम नॉट चेंजिंग द पोलराइजेशन स्टेट in that sense. It is still circularly polarized light. I'm only interested in changing the handedness. So when I want that, I'll use a half wave plate. Think of half wave plate like a minus sign. Okay. So if I want to, it's like माइनस ही आ रहा है बिकॉज इट्स पाई का फेज डिफरेंस है ना. सो राइट को मैंने लेफ्ट में करने के लिए आई जस्ट नीड वन माइनस साइन बिटवीन दीज टू कॉम्पोनेंट्स, दैट्स ऑल. सो elliptical light में भी क्या होगा? if the incident light is elliptical light, I will still maintain elliptical light on the output, but now the handedness of the elliptical light would also get changed, that the right would become left elliptically polarized and the left elliptically polarized would become right elliptically polarized. Okay, so we can write that right elliptically polarized light, REL लिख दिया मैंने. What this means is right elliptically polarized it falls onto a half wave plate. So on the other end, I will get a left elliptically polarized light, okay? So I'm getting a LEL, which is not a terminology, but I'm just writing a short form. So I will basically make it into left elliptical. So similarly, if I will have a, matlab you are understanding, if left would be incident, then it will become right elliptical, okay? So now next we have to discuss a quarter wave plate and what would happen when different types of lights are incident on a quarter wave plate. So quarter wave plate karta hai fir, this was the, okay, so C here that we are dealing with a quarter wave plate written as QWP. So here del phi is equal to what? 90 degrees. So it is 1/4 of the total 2 pi. The 2 pi ka 1/4. Quarter is 1/4, right? So that is how you can remember the names. Half wave plate is half of the 2 pi. So del phi is 90 degree, and therefore I can write the lambda jo hai, uske liye I can write that D NO minus NE should be equal to 2m plus 1 lambda naught by 4. Is it correct? 0 is lambda by 4, then 1, 3 lambda by 4. Okay. So यहाँ पे I am interested in a relative phase shift of lambda naught by 4. Lambda naught by 4 corresponds to del phi is equal to 90 degree, right? So here my m can be 0, 1, 2, and so on. Okay, so again, I can write a formula for this also. This should be equal to 2 pi by lambda naught into this. So ये formulas हमें याद होना चाहिए that what is the, even if you don't, पता है mostly questions में क्या होगा, m का factor तो हमेशा 0 ही होगा. They will always ask you lambda by 4 या lambda by 2 के लिए क्या मतलब what are the parameters that are required. So this is a general formula, but you should at least remember this कि phase difference 90 होता है, which corresponds to lambda by 4 in terms of path difference. इतना तो याद करना ही पड़ेगा कि एक अगर full मैं wave consider कर रही हूँ तो ये this full wave corresponds to lambda, this thing, and this also corresponds to 2 pi. This whole length also corresponds to a phase gain of 2 pi. So because this point here, this A point is in phase with B point, therefore ये lambda distance चलने के लिए 2 pi का phase gain हुआ होगा, ठीक है? And therefore this point, if I consider C point, this distance should correspond to a phase change of pi. And therefore this pi is corresponding to what? Lambda by 2. So like that you can remember कि optical path difference lambda by 2 होना चाहिए. Or if I consider this point, so this is some D point. So this should now correspond to a phase change of pi by 2. So this pi by 2 should now correspond to lambda by 4, like that, okay? So itna I should remember that when I'm talking about a phase difference of 90, then in terms of optical part difference, that means a part difference of lambda by 4, okay? So अब जो quarter wave plate है वो काफ़ी useful चीज़ होती है because we can use a quarter wave plate to convert a plane polarized light into circularly polarized light and a circularly polarized light back into plane polarized light. So it is one of the most dynamic elements in that sense, and it is very widely used in almost all optical labs. Even I have used it in my experiments. So let us look at what we will get. So in a quarter wave plate, let us do case number 1. So case number 1 is when the incident light is in P state. or plane polarized light. Okay, so again, let us say this is my quarter wave plate. And I have some P state. So isme what I've done is I have chosen the optic axis to be, like this. That, how do I say? Like this is my optic axis right now. Okay, so in this direction, sort of like in the Z direction. That is how I've drawn here. I don't know why I've drawn it like this. But maybe you can also, let us do it the other way, just pehle kiya tha na, because that was making sense to us. So let us say that the same coordinate मैं draw कर रही हूँ. So I'm taking the optic axis again like this. So optic axis is this. Okay, and I'm just looking at this from a side. So now I have a plane polarized light, which is sort of falling like this, and it is making some angle theta again with the optic axis, same configuration जो पहले था. But अब क्या है? There are two cases that can happen on the output. So the first case is, so ये P state का electric field लिख देते हैं पहले. So यहाँ electric field है that I have EOX I cap plus EOY J cap, the whole thing multiplied by cos of kz minus omega t. ठीक है? This is what. Okay, so this is what is incident. So now first thing जो हो सकती है, so I can have the first thing that theta is equal to 45 degree. That this beam is actually making a 45 degree angle with respect to the optic axis. So then what will happen that and also if my EOX is equal to EOY, अगर ये दोनों जो है इनका magnitude same है, EOX amplitude and EOY amplitude दोनों के दोनों same है. So if this is true and these are also true, that their magnitudes are equal, then what will happen is on the output, after passing through this, what will happen is quarter wave plate क्या करेगी? Quarter wave plate इन दोनों components में से किसी एक component में pi/2 का phase difference introduce करेगी. ठीक है? So pi/2 का phase difference introduce करने का क्या मतलब है कि इसको मैं ऐसे भी लिख सकती हूँ. ये cosine थोड़ा visualize नहीं हो पा रहा है ऐसे. So what I can write it, I can multiply cos with each of this, then it's easier. So this is cos of kz minus omega t I plus EOY, no, not sine, cos of kz minus omega t j. Okay, this is what is incident. Cos of this is multiplied with both. Now I'm saying that EOX is equal to EOY is equal to some E0. They have same magnitude. So that means, let us say कि मेरा जो jth component है, ये वाला जो component है, this gains pi/2 phase. ठीक है? So उसका मतलब क्या हो गया? That this is some E0 है ये. I am considering right now that this is E0 and this is E0. That means they are same. Okay, so this is E0 cos of kz minus omega t plus pi/2. So what will it become? क्या बनता है ये? pi/2 से this will become E0 sin kz minus omega t and a minus will come. है ना? Cos of x plus pi/2 क्या होता है? I think minus sin x होता है. So this is what I'll get. So that means कि मेरे पास half wave plate से जाने के बाद क्या मिल रहा है मुझे? I'm getting E is equal to some E0 because I have assumed that EOX is equal to EOY is equal to E0. So I will get I cos kz minus omega t minus j sin kz minus omega t what is this? This is the expression for a LCP. It's a circularly polarized light, and that to a left-handed circularly polarized light. Okay, so depending on the theta and depending on the orientation of the optic axis, that I या J में से किसी एक component को pi/2 का phase difference मिलेगा extra, and because of that यहाँ पे मुझे output में क्या मिलेगा? Output में I will get a circularly polarized light. ठीक है? And this circularly polarized light can be left-handed or right-handed. So that is up to me, that how I design my system, how I choose the optic axis, and how do I make sure ki which of these components actually, matlab, how the orientation is there. Right now, orientation aisa tha, aisa bhi kar sakte hain. I can already choose the initial plane polarized light so that, you know, I have a minus here rather than plus. That's up to me what beam I'm incident, kya incident kar rahi hu main, and then I'll get a RCP light on the output. Okay, so all these things are free for us to choose. So this is case number 1. So what we saw कि एक कोई P state था, वो quarter wave plate पर incident हुआ, but if the theta that this P state was making with respect to the optic axis was 45, and if the amplitude of its X component and Y component was same, then we ended up getting a circularly polarized light. And the second case is that this theta is actually not equal to 45 degree, and there is no relationship between EOX and EOY. Uska value kuch bhi ho sakta hai, equal bhi ho sakte hai, unequal bhi ho sakte hai. They are free to vary. Okay, so in that case, what will I get? I will get an elliptically polarized light on the output. So I can use a P state, input P state, to produce a circularly polarized light or an elliptically polarized light. Okay, so in that way, a quarter wave plate is a extremely useful retarder. It's an extremely useful optical element in optics lab, because you can actually change P state बनाना बहुत आसान है. Polarizer का सिर्फ मुझे theta change करना है, and I can choose what P state I want to make. But then from that P state to make a elliptically polarized light भी बनाना आसान है. It's the most general case, but circular बनाने के लिए its quarter wave plate is the most useful element. Okay, so case number 2 हो सकता है that now I'm considering that the incident light is actually a circularly polarized light. So I'm considering that the incident light is actually a circularly polarized light. So quarter wave plate के ऊपर जो light incident हो रहा है, that is a circularly polarized light. So then what will I get on the output? So यहाँ पर भी मैंने लिखा नहीं, यहाँ पर भी डेल्टा क्या है? Delta is pi/2 only. So delta is the phase difference on the output side. Okay, so now this delta is going to be different in this case. Then you will understand why I'm using the term delta. So let us say that I have a circularly polarized light. So circularly polarized light की दो बातें क्या होती हैं? That the theta it's making with the optic axis is 45 degree. Okay, and the second is कि उसके जो components हैं, उसके जो अपने components हैं, उनके बीच में जो phase difference है, let us say that is phi, is equal to already pi/2. So what I mean is एक cosine kz minus omega t था, look at this equation, and दूसरा sine था, तो already there was a pi/2 phase difference between the two components. And the third is that the EOX is equal to EOY is equal to E. Okay, all these contribute to a circularly polarized light. So अब ये इस type का एक light quarter wave plate के ऊपर incident है. So what should I get on the output? So see now, if I write this, let us write the expression so that we can understand better. So this is kz minus omega t plus j. So this can be plus minus depending on RCP or LCP. मैंने क्या choose किया है? So sine kz minus omega t. So this is what is incident. Okay, this is what is incident on the quarter wave plate. So now quarter wave plate क्या करेगी? Quarter wave plate is going to introduce a phase difference of pi in either the x component, pi by 2 in either the x component or in the y component. ठीक है? So अब क्या होगा कि एक तो ऑलरेडी x और y component के बीच में pi by 2 का phase difference है. ठीक है? Already they are at a इनपुट में ही एक कोसाइन है एक साइन है. ठीक है? तो अब ये हो सकता है कि अगर मैं जो x कंपोनेंट है जो कि कोसाइन कंपोनेंट है उसमें मैं एक और पाई बाई 2 का फेज ऐड कर दूं, उस कंपोनेंट में मैं ऐड करके उसको साइन बना दूं, या फिर साइन कंपोनेंट में मैं एक और पाई बाई 2 ऐड करके उसको कोसाइन बना दूं. आर यू अंडरस्टैंडिंग? एक बारी में दोनों कंपोनेंट में से किसी एक में ही पाई बाई 2 ऐड होना है, एंड वो किस में ऐड होना है वो डिपेंड करेगा कि ऑप्टिक एक्सिस कैसा अलाइंड है और 10 चीजें. ठीक है? बट after passing through the quarter wave plate, one of these two components will get a phase difference of pi by 2. ठीक है? extra pi by 2. already उनमें pi by 2 का phase difference है. so ये जो डेल्टा है कि आउटपुट में उनके बीच में क्या डिफरेंस रह जाएगा, that is either going to be equal to 0 or it's going to be equal to pi. so what I mean by pi is कि ऑलरेडी पाई बाई 2 था, उसमें पाई बाई 2 ऐड होके वो पाई हो गया, या फिर वो एक में पाई बाई 2 था, एक में दूसरे में भी पाई बाई 2 ऐड होके दोनों का फेज डिफरेंस 0 हो गया. Are you understanding? So delta in both cases, what will I get on the output is I will get on the output is a p state, because think of it like this कि या तो मैं इसको करूं that it becomes sin kz minus omega t plus pi by 2, and then I convert it into cosine. ठीक है? So this will actually give me, if I will add here, it will give me cos of kz minus omega t, right? So this is like I am दोनों अब in phase आ गए. ठीक है? I component is I cos kz minus omega t और jth component भी cos kz minus omega t हो गया. But if rather than doing that, मैं अगर इस कंपोनेंट में पाई बाय 2 ऐड करूं तो आई विल गेट कोसाइन ऑफ kz minus omega t plus pi by 2, which will give me minus of sine kz minus omega t. so उस केस में ये यहाँ पे कंफ्यूज होते रहोगे, इसको प्लस से लिखती हूँ. लेट अस कंसिडर दिस ओनली. सो अब क्या हो गया? फर्स्ट कंपोनेंट हो गया माइनस I sin kz minus omega t plus j sin kz minus omega t. ठीक है? सो अब ये माइनस साइन का मतलब हो गया that I have in a way added an extra phase difference of pi between them. So this delta means that in that space. Okay, quarter wave plate हमेशा pi by 2 ही ऐड हो रही कर रही है, but depending on कि दोनों में से किस कंपोनेंट में ऐड हो रहा है, आउटपुट में मेरे पास जो p स्टेट आएगा उसका बेसिकली ओरिएंटेशन में एक माइनस साइन आ रहा है या नहीं आ रहा है, वो बेसिकली 0 और पाई डिनोट कर रहा है कि वो ओरिएंटेड कैसा है पी स्टेट. ठीक है? बट व्हाट यू हैव टू रिमेंबर इज कि अगर इनपुट में मेरे पास में सर्कुलरली पोलराइज लाइट है, सो आउटपुट में इट इज गोइंग टू गिव मी अ पी स्टेट. ठीक है? बिकॉज ये दोनों बोथ ऑफ देम विल कम इनटू फेज, so it will give me a p state in the output. ठीक है? so अभी आज मैं क्लास यहीं पे खत्म करती हूँ. क्वेश्चंस तो हम स्टार्ट ही नहीं कर पाएंगे, बट ये चीज समझ आई है या नहीं आई, बिकॉज ये थोड़ी इंपॉर्टेंट है. थोड़ा इसको सोचना कि कैसे हो रहा है ये, बट ये हमें ये तो याद ही करना पड़ेगा जो आज की क्लास में डिस्कस किया है. इसमें यू कैन नॉट मेक अ मिस्टेक. you have to remember कि half wave plate क्या करेगी, it will not change the type of beam. p state ही रहेगी, it will just get rotated. circular light या elliptical light क्या होगा, उसका handedness change हो जाएगा half wave plate में, but quarter wave plate is the one which will change the state of polarization. so quarter wave plate will convert a p state into a circular light and a circular light into a p state, like that. Okay, so Aj, I have to go somewhere, so I'll stop the class now. So ठीक है?
Good night, ma'am, and thank you, ma'am.
ठीक है, good night, bye bye.